Okay, this is a video about identifying symmetry in polynomial functions. A challenging concept from the first unit was to determine whether a function was even or odd in terms of symmetry. That's different from identifying whether the degree of a function is even or odd, and we're going to explore that idea in this video. So what you may remember from the first unit is that you can describe an even function if a horizontal reflection is equivalent to the original graph, which means the graph would be symmetrical around the y-axis. And you can identify an odd function if it satisfies this property, where a horizontal reflection would result in the same graph as a vertical reflection. And that's described as symmetry about the origin, or rotational symmetry. So without graphing, we're going to take these polynomial expressions and we're going to test them to see if there is symmetry. So for our test, we need both the original function, we need to see what f at negative x would look like, and we need to see what negative f of x would look like, and then we can do some comparisons. So f at negative x means we're going to replace x with negative x and simplify. So that would be 2 times negative x to the exponent 4 minus 5 times negative x squared plus 4. And if we raise negative x to the exponent 4, that'd be 4 negative x's being multiplied, which would make 2 pairs of negative x's, and negative x times negative x is positive x. So that would just result in positive x. So this would simplify to 2x to the exponent 4. Same thing happens here. Negative 5 is your leading, or is your coefficient, not your leading coefficient. Negative x squared would be negative x times negative x, which would just be x squared, and then plus 4. So what you can see happening here is that these two exponents were even degrees, and when we inserted a negative x in the place of x in a even an even powered exponent, an even exponent power, that's better, we come out with just the original function, or the original term in this case. What about putting a negative in front of f of x? Well, that means take the whole function and multiply it by negative 1. Well, that would result in negative 2x to the exponent 4 minus 5x squared minus 4, plus 5x squared, sorry. And that switches the sign of every term in the function. So now we can make some comparisons. We have our original function is equivalent to f at negative x, which means we have a even function. And f at negative x does not equal negative f at x. Therefore, it's not odd. So we do have an even function here. Let's try another one. G of x. G of x is negative 3x to the exponent 5 plus 9x squared. So let's do some tests. Let's see what g at negative x is. That would be negative 3 times negative x to the exponent 5 plus 9 times negative x squared. Negative x to the exponent 5. That exponent's odd, so you're going to have an odd number of negative x's multiplying, which means our answer is going to be negative x to the exponent 5. Negative x to the exponent 5 times negative 3 would make positive 3. So we'd end up with 3x to the exponent 5. We have an odd exponent, so that means there's an odd number of negative x's being multiplied. 2 pairs of them would make positive, but there'd be 1 negative left over, and that would have to multiply the leading coefficient, negative 3, and make it positive. Plus 9 times negative x squared. Negative x squared is just x squared, so we have 9x squared. And negative g of x means take a negative and multiply it by the whole function. And that would switch the sign of both terms, so we have 3x 5 minus 9x squared. So now we can make our comparisons. Our original function, g of x, is not the same as g of negative x. So therefore, we're not even. And g at negative x is not equal to negative g of x. Therefore, we're not odd. We are, in fact, neither. One more, and then we'll draw some conclusions here. H of x. To test for even symmetry, we need h at negative x. So we're going to replace x with negative x. So we get 2 times negative x to the exponent 5 minus 5 times negative x to the exponent 3 plus 4 times negative x. Negative x to the exponent 5 would leave us with an odd number of negative x's, which means we need to change the sign of the coefficient. Same happens here with 3. And same thing happens here with degree 1 term. So you might be starting to see a trend here. So I'm going to pause right now just to kind of reflect on what might be happening or what you might be picking up on. Notice that the odd exponents end up keeping the sign and flipping the coefficient of each term. 2, negative 5, and positive 4 became negative 2, positive 5, and negative 4 when we inserted negative x, because the exponents worked out evenly. The opposite's true, the exponents worked out odd. The opposite's true when we look at even exponents. 4 and 2, when we inserted negative x, came out positive, and the coefficients didn't change. Interesting. If we look at negative h of x, that means take the whole function and multiply it by negative 1. The result here is that each of the term signs are going to change. And each of the terms signs changing was the exact same thing that happened up here when we inserted negative x in the place of x. The reason it happened up here was because each of the exponents were odd. The reason why it happened down here is because we multiplied the whole function by negative 1. So realistically, these are the same thing. And when h of negative x equals negative h of x, that means we have an odd function. And let's reflect on that one more time here. We get an odd function when each of the exponents on our powers are odd. Because when each of the exponents on our powers are odd, we end up flipping the sign of each of those terms, which is the exact same thing as multiplying the whole function by negative 1. So I think we just came up with a conclusion here. Let's reflect on whether it's even or not. The original function is not the same as h at negative x, therefore it's not even. So it's interesting. I think we have a conclusion here. When we have only odd exponents in a function, only odd exponents, no coefficient, no constant term, just terms with x and odd exponents, we have an odd function. And by an odd function, I mean odd symmetry. Let's go back here and look at the even function. This one was even. Let's take a look at the exponents. 4, 2, and this would be technically x to the exponent 0, right? Because the exponent on the x term here is 0, that makes it 1, and 1 times 4 is 4. So it's like x to the exponent 0 term. Even, even, and even. All of these exponents are even, and this function ended up even. And the reason why is because, well, when you insert negative x into a term that has an even exponent, it comes out with the same sign. So I think we have a conclusion here about even functions too. Let's bring it all together down here in our conclusions and kind of restate what we just said. Some even degree polynomials are even functions. What's that mean? This is a degree 4 polynomial because the biggest exponent is 4, and it was an even function. Some odd degree polynomials are odd functions. Well, let's look at that. This is a degree 5 polynomial, which makes it odd because the exponent's odd. So this is an odd degree polynomial. And it turned out that it had odd symmetry, therefore it's an odd function. But this one is also an odd degree polynomial because the largest exponent's 5. This one did not turn out odd. So what's the difference? Well, the difference is that even degree polynomials that end up as even functions or have even symmetry has every term in it with an even exponent. And therefore, it would satisfy the even property and make it an even function. So that means if every exponent in a polynomial is even, we'll have an even function, whether or not we have a constant. Same's true for odd. All odd degree polynomials that has odd exponents will be an odd function. The tricky part here is if there's a constant, it's not an odd function, and you have to watch for that, because that constant would be your x to the exponent 0 term, and we'll consider that even for this property to remain true. Okay? So no constant. Tricky concept, but we're going to explore it a bit more in class tomorrow. Thanks for watching.